You might be wondering what this canister of de-icing salt is doing in a physics lab.
We've
put together a small demonstration to determine the radiation levels of concentrated de-icing salt, potassium chloride.
David Breitenmoser is a physicist. He doesn't normally perform measurements on de-icing salt. Instead, he develops complex computer code to identify radioactive sources. He is making an exception for us to demonstrate the capabilities of this detector by measuring the faint radiation emitted.
There it is, a beautiful peak. This is potassium-40. The de-icing salt is radioactive.
There is a reason why the detector is so sensitive. Normally, it sits in the belly of this Swiss Air Force Super Puma helicopter. Every year, the helicopter flies across Switzerland, measuring background radiation levels, for example, and monitoring the environment around nuclear facilities. To carry out these aeroradiometry measurements, the helicopter repeatedly flies over the defined terrain along parallel paths at a height of 90 meters above the ground. The detector scans an area with a radius of about 300 meters at speeds of up to 100 kilometers per hour.
The radiation is attenuated and scattered by the Earth's atmosphere, so that only a very small amount of it actually reaches us in the helicopter. That's why our detector has to be so sensitive.
Can the detector also measure the amount of radioactive material present?
This is actually the big challenge that we are trying to overcome with our research at PSI.
What the helicopter detects is a few isolated high-energy photons. These are emitted by the source in all directions. The more radioactive material is present, the more photons are detected. But how can the amount of radioactive material be calculated from the signal?
In order to deduce how much radioactive material is present, we would first have to calibrate the detector. This would mean dispersing various known radionuclides across a large area and then measuring them to find out exactly how the detector responds to these signals. But nobody wants to do that, of course.
David uses a complex computer model to calculate the amount of the radioactive material from the signal without having to use radioactive samples. For example, what happens to the signal when the photon hits the detector at a different angle? Or if the source is not a single point, but an entire surface? David has to take all these parameters into account in his computer model.
It takes about a day to run a simulation on our mainframe computer here at PSI. If we wanted to calibrate this detector for every possible combination, we'd have to run more than 1 million simulations. That adds up to more than 1,000 years of simulation time.
1,000 years? Despite using a mainframe computer? That's definitely too long. David's solution: split the problem into 2 separate simulations and put them together again at the end.
By simulating the possible detector signals and the environmental factors separately and only combining them at the end, we are able to reduce the computational effort by a factor of 10 to the power of 6. In other words, we are 1 million times faster than before.
Thanks to David's trick, it's possible to run all the necessary simulations, which would normally take 1,000 years, in just over 2 weeks. This means he and his team can use a normal laptop to determine how the detector will respond to a radioactive source. David and his colleagues have successfully tested their new computer model in a field trial. In theory, it could even be used to determine the amount of salt used on winter roads.